All right. So today's going to be kind of a different day. I mean, we've had a couple days that are, primarily focused on lecture and concept. But usually we have a lot of breakouts, right? We have a number of breakouts as we go forward. Today's not going to be really like that. Today is going to be more, let's look at a machine learning workflow and think about this conceptually. I'll ask you questions as we go forward, just, kind of thought-provoking questions. I'll be showing something, demoing something, and then I'll say, hey, how does this work right here? Or what do you think is going to happen in this moment? Just to kind of test intuition and see where you're at in understanding as we go forward. Today, we're going to cover these topics, right? And really, we could break this down to really two topics. We're going to talk about Markdown and maybe some higher level ideas in note taking, and then we're going to talk about machine learning. And there's some intuition that is good to have when you start the DSI regarding a concept called cross-validation, which is just everywhere, right? We're always looking to validate the machine learning models that we're using, and that can look a number of different ways, but we're going to focus on a very simple form of cross-validation. And then I'm going to outline kind of a general machine learning workflow, something that the code that I make here, you could take and you could find a different model and you could plug that model in and it would work. Or maybe you could go find some other data and modify the code a little bit and use, some model on some data. But it'll be a generalized approach for what I'm going to call supervised learning. And we'll talk just a little bit about supervised and unsupervised learning and kind of a couple just paradigms within the data science space. So with that, also, let me just point out that I'm not going to be pasting code in today into the Slack. If you want to follow along with code, those two links that are in the post for today's class, you'll want to grab, especially that second one, okay? Especially that second one if you want to run a Jupyter Notebook locally, or that would really be the option if you can run a Jupyter Notebook locally, or if you can put the data up on Google Cloud, Google Colabs, that is. That would also be an option, although I think that would be a little bit tedious and it would be hard to keep up. What I'm recommending for today is, unless you can run a Jupyter Notebook locally and you know how to do that, don't worry about coding this stuff out. It's more about looking at this, analyzing it, getting a sense of, getting a higher level view of these processes. So with that, let's talk about a couple things. So a lot of people will ask me as they're going into the DSI about note-taking strategies, and the first suggestion, the primary suggestion I make for anybody is start learning Markdown. And I'm going to just demonstrate what Markdown is. So I've got a couple files in here, right? I've got this markdown example.md, and then I've got this Python notebook. And you can tell it's when I say Python notebook, it's the same thing as a Jupyter notebook. We used to call them Python notebooks. Now we call them Jupyter notebooks. It's the same thing. But they have this extension IPYNB. So I'm going to just code. I'm going to open this Markdown example file that's sitting here. And that is somewhere here. Okay, there it is. Also, if you have VS Code installed, you can actually open Jupyter Notebooks within VS Code. That's what I'm going to do. It's a little bit nicer, I think, than running a Jupyter Notebook in a browser, but I'll also open it in a browser just to show you that you can do that. And there are other things like Jupyter Lab, but I'm not going to get into that here. There's kind of a lot of different tools within the Python environment. So let's talk about Markdown. And I don't need the terminal for this. So Markdown is, you could consider it to be a document formatting language. And we've all used something like Microsoft Word or Google Docs or something like that. And after you use Markdown for a little bit, you'll find those word processing programs to be a little bit cumbersome, probably. We're sort of stuck with those because of various workflows at our jobs and other things. But Markdown is kind of remarkably similar. Now, what makes this a Markdown file, offhand, is that the extension here is .md, okay? Markdown example.md. And let me just show you something really quick. Notice, so this is our repository for the course. Notice in the repository, there's this file readme.md. That's a Markdown file, right? So that's what this whole thing is. All of the the links that are here, the bold type headers, these HR lines, these horizontal lines. Everything that's in here, and we could put images in there. We've got these bullet points. We've got what else is in here? That's really about it. But I'll show you a couple more things. If we were to look at this, like if I click on Edit right here, we can see that this is also a fairly readable format. Even when it's in plain text, even when it's not being rendered as Markdown, it's fairly readable. And that's part of the goal of Markdown. It's to be readable when it's in its raw text format, and it looks nice in a rendered format as well. Reasonably professional. You can put links in there. You can put HTML in there, and that makes it really, pretty capable of covering a lot of ground. So I'll go ahead and not change this file at all. And I'll just sort of start from scratch with ideas in Markdown. If you're using VS Code, you can hold Shift, Command, and hit V, and that'll make a preview of the Markdown. Now, notice there's nothing in this, of course, because I haven't written anything in it. I'm going to split this to the right, and then I'm going to move it over there. And anything I type here is going to show up over there, right? And then I can get a preview of the thing I'm working on. So let's just play around with Markdown a little bit. So if you use a single hash mark, this is the largest header for the text that follows it. So this is the largest header. And then, here's another with 2 hash marks. This is a slightly smaller header. And, if you follow this logic, let's take this out to, say, 1, 2, 3, 4, 5. This is a small header. And already you can see that this is pretty dynamic. Here's some text. And this small header looks to be about the same font size as that text. And if I do something else here, like here's some bold text, if I want this to be bold, I can put 2 stars around it. And that looks to be the same as that smallest header as well. Okay. And you know, you can do other things. Of course, you can have italic text. So you know, 1 asterisk is italic, and of course we can see that right there. 1 asterisk is italic, and you know, we can also do underscore an underscore, right? An underscore will italicize, and that's equivalent, right? We're seeing the same thing. So there are a couple different ways to do a lot of things here. I think one of the very helpful things, or I'll just keep showing some helpful things. So if I want to make a line, just like a horizontal line, I can put a bunch of dashes. So if I want to make slides, for example, here's a little secret about our slides. They're all written in Markdown. And we did that because we had everything in Google Slides at some point, and to go through and revise them would take days, you know, to do a pass on like 5 slide decks. And in this case, if I want to make a slide, you know, here's a slide topic, and then you know, item 1, item 2, item 3, and a sub item, right? Sub item 1, sub item 2, and so on. So this makes a very simple, easy to construct slide deck, and we just find that a lot easier to maintain as we evolve the materials, right? So these are some, you know, fairly simple, fairly powerful things. One of the things that I really love about Markdown, you can make a code cell. So let's make a slide that says make a code cell, and using tick marks. And tick marks are they look like this, right? You see this? It's not a single apostrophe. It's the thing above your tab key. It's the thing that you use when you paste code in when we have a challenge, right? So using tick marks, if you do triple tick marks here, 1, 2, 3, type Python, this will actually show Python code in a friendly way. Let's say a friendly way. It'll have highlighting of the text. So some function, or let's do factorial, right? So the factorial of n. And what we're going to see over here is code that renders nicely. It's not runnable or anything, but if you copy and paste it from here into another space, including, you know, a word processing document or anything like that, it's not going to have special characters. It's going to render in this kind of universal format that we use in text editors, UTF-8. So I'm going to say, you know, product, and for num in range 1 to n plus 1, and then prod gets num, and we can return the product. So that's nice, right? What this means is that you could make a notes document that is well organized very quickly without that has copy pastable code, right? So if you have what I suggest in general, what I suggest is that you make a single document, a single Markdown document for taking notes. And the reason I suggest that is that you can put everything in there. You can put your conceptual notes, you can put your Python code, and you can also, and I'm going to demonstrate this in a second, you can also put your mathematical formulas. So let's demonstrate that. I'm I'll just make a slide for, let's say, Poisson. And one not great thing about this preview over here is that you can't scroll down to center things, which is a little frustrating, but not a big deal. So let's call this Poisson PMF, and let's say given an average rate, and notice this if I say lambda. So this is LaTeX. Actually, this is what we call MathJax, but it is a markup language that allows you to write mathematical formulas, right, or mathematical formulation. And it can get fairly complex, but it's not so bad. And once you get used to it, it's really great, actually, because you can, you don't need to go searching on the internet to find this symbol, the lambda symbol. You can just type \lambda within $signs, and that'll render properly. Now, something to be aware of, if you do this on GitHub or documents that are on GitHub, if you do this with documents on GitHub, you'll need either a special plugin to have that MathJax render properly in your browser, and I believe I linked that plugin. Let's see, it's a Chrome extension, and I think, yeah, it's definitely in the documents, in the README. It's one of the first things under other helpful resources. Otherwise, if you want people to be able to read your rendered MathJax, they have to look at an HTML version of your Markdown documents, which you can provide. There's just a different path. You don't need the Chrome extension for it to render in VS Code. VS Code will render it by default. So that's nice, right? Sometimes it crashes and you have to restart VS Code. That's a little bit frustrating. Like, it was very possible that this wouldn't have rendered and it just would have shown this $\lambda$. But, yeah, you might need to restart VS Code, but I think it should render by default. If it doesn't, I can look into it at the end of class, and we can just see if there's a quick troubleshooting. Yeah, we'll look into it at the end of class, because maybe there is some plugin that I've enabled here that's built into VS Code, but I don't remember doing that, and I use a few different computers. I don't remember ever doing that. I might be wrong though. So I'll go ahead and finish out this slide. Given an average rate lambda, find the probability of some number of events, k, right? And even though, this is maybe what I would do, I would say, I just want k to render in a similar way to that lambda. And then I can say, here's the PMF, and I'll just write a slightly different version of this. So if I want this inline LaTeX, then it's $. If I want a block of LaTeX, it's the $. And I can say the probability that how do I want to frame this, of x, and actually let's say probability of /lambda and k, yeah, let's do it like that, is going to be e. Notice I'm using a caret here instead of the double stars, double asterisks. Most languages use a caret for exponentiation, and I'm going to say e to the negative lambda, and then times, I'm actually going to say times, well, I prefer c dot personally, times for times. So e to the negative lambda times lambda to the k. And this is all going to be over factorial of k, right? And the way that you can construct a fraction here is with this slash frac. And that'll get us our numerator within these curly braces. And then the denominator can go here, so over k factorial. So that's kind of nice, right? It just, we can build our mathematical formulas, and you can practice by going and translating mathematical formulas that you find, things that you want to have a quick place to look up. This is just very convenient for that. So, you know, everything can go in one document. The reason why I suggest everything go in one document is it may fly in the face of organization, but when you're in a boot camp, when you're learning, when you're trying to learn as much as you're going to be trying to learn in the limited amount of time that you're going to have to learn it, it's very helpful to be able to go to one place and look up everything that that you deem as being important. The other really important thing is to be able to Google stuff really fast, and you become much better at that in a boot camp. You know, many of you, I'm sure, are great at Googling things. Like, how is that even a skill? But it turns out that it is a really important skill. And when you're in a boot camp, you're like, well, how do I look for this thing? And the way that you look for that thing is you ask very specific, well-worded questions, and you have to think kind of how other people might think without knowing how they think, right? So you end up inventing new ways of asking questions, and that leads to finding information very quickly. You know, that said, there are some places where you'll go, and I'll show you one of those places right now. There's this really amazing thing called archive. So this is just a massive database of papers, of academic papers in math, computer science, physics, obviously quantitative biology, finance, statistics. There's a couple of different places where machine learning shows up under statistics, I believe under computer science as well. There it is. And, you know, why does it show up under one or under the other? Well, I don't know. And then there's audio and speech processing, signal processing, which are showing up under electrical engineering. You know, this is more where my skill set is in signal processing, image and video processing, wave processing, things like that. And then, you know, natural language processing is my academic background. But I'll paste this in, and I just want to demonstrate what I mean by Googling well. So let's say I want to find something on latent Dirichlet allocation, which currently I'm doing a project with. You don't need to know what that is, but I'm going to say citearchive.org, and I'm going to spell it correctly, and I'm going to just look up latent Dirichlet allocation. Google is going to do, well, it's weird because actually the search engine in here is not bad. You can look stuff up in here and that's fine, but I still think Google does a better job with traversing this. So here's an article from 2020, improving reliability of latent Dirichlet allocation by something, and you know, I might open this here, and here's the abstract. And if I want to see the PDF, all these PDFs are available. If it's on archive, the PDF is available. There's no wall like with JSTOR or any of the other major journal databases. And arguably, this is one of the, well, for us, this is the most important journal database that's out there at the moment. So yeah, here's this paper. And, you know, it's possible that this paper only exists on archive and that it's a very minor publication. But you know, we don't know that unless we look into the authors and, you know, various other places. So this name is misspelled, I think. This is a pretty famous person right here in the data science world, but they're Agarwal, not Agrawal. Anyway, this I'm just trying to give you a sense of where you're going, how you're going there, and some tools that could be helpful. I really am a big proponent of learning Markdown very soon. It's super easy. As you can see, this is not hard at all. And, you know, very simple syntax. You can use other files to, you know, to kickstart you in this. And I think that's really helpful. So I generally start off with talking about Markdown. Well, for one pretty big reason, we're going to be working in a Jupyter Notebook, or I'm going to be working in a Jupyter Notebook today, and a lot of that is going to be inside of Markdown cells within a Jupyter Notebook, which is pretty amazing that we have an environment where we can do that. So maybe what I'll do first, I'll type Jupyter Notebook in my terminal. I have Anaconda installed, so this is actually going to open a server on my machine. And here's a browser showing the you know, what's in that server. And here's this notebook, the notebook I'm going to be working in, simple cross-val and ML intuition.ipynb. And if I click on this, this is a Jupyter Notebook, right? It says not trusted. This doesn't really matter for us right now. I'm just making it trusted. There's some things to notice, right? This is using the Python 3 kernel, right? You can actually have a notebook that supports Python 2 if you have Python 2 installed. Not a suggestion, but it's something that sometimes you'll need to do. These cells, we can modify these. And currently this is a code cell, right? We've seen this already. So if I print hey and I run this, I'm running it by holding Shift Enter or Control Enter to run it in place, right? That's in place. This is a code cell, but if I hit Escape and I hit M, I actually turn that into a Markdown cell, which is pretty cool. And just notice, you know, this is now Markdown, and that renders as Markdown, and that's really nice. That's really nice. So here's a thing: why wouldn't you just take all your notes in Jupyter Notebooks, right? Why wouldn't you do that? The short answer is if you always have to spin up a server to look at your notes, that's not great. That's going to be a little frustrating. However, with VS Code now, you can, I'm just going to quit this server. With VS Code now, you can run a Jupyter Notebook within it. So that does sort of clear that up a little bit. You could take notes in a Jupyter Notebook within VS Code, and that'll be a little bit better. I'm surprised that didn't save. I guess I didn't hit save, so that's probably why. I'm going to work in this Jupyter Notebook within VS Code, and here's kind of a cool thing though. If you do take notes, if you do save things in a Jupyter Notebook, you can save this out to Markdown as well. I believe maybe there's an export. You know what? I think I'll have to do that from the browser. So this is a fairly common thing to do, where you write a bunch of stuff here, right? I'll just print hey again, and you know, just make some Markdown really fast. So Markdown. If I go to File, Download As, it gives me the option to download this as HTML, to download it as a Markdown file, or a PDF. Although the PDF often doesn't render that great, you know, You have to mess with it a little bit to make it work well. You can also download this as a Python file, which that's really cool if you are proofing something in a Jupyter notebook. And the reason you might do that is you get immediate visual response, right? You can make a plot really quick and see the result of it. If you do that work within a Jupyter notebook and then download the whole thing, if this stops glitching out. Okay. Let me just, there we go. So if you go download as a Python file, you actually get a .py file, and that's a runnable file. And you can go in and clean it up and do whatever you need to it. That is some people's workflow in terms of development. And they use, some people will use Jupyter Notebooks as their primary coding environment. I don't personally suggest that. I think it becomes a bit of a crutch. But when I'm doing exploratory, something exploratory with data, I will almost always use a Jupyter Notebook. The reason being I can just look at everything. And we'll see that in a little bit as we start to get into this. So, you know what? Maybe I will use this. I'll use this environment. I think it will operate exactly the same as in VS Code, but I think this will be nicer for today. So I'm going to just delete a couple cells, and we'll start at the top of this. All right. So let's start thinking about machine learning, just generally. I know that some of you have a stronger sense of what that phrase means, and I think some of you, it might be mysterious. And I want to kind of give a basis for how to think about machine learning. Often we'll call this ML, right? Machine learning. If you see DS, right? Data science. If you see DE, data engineering, we don't have enough time to say the whole word, right? But I almost never say ML. I almost always say machine learning. Because people don't know what ML is when you just say ML. But let's think about ML as ways of recognizing patterns. Well, let's start there, right? So if we have some kind of, let's say we have a plot and we have a bunch of points, and this is just, let's say we've got a bunch of points over here, and then we've got a different class of points. I'll use green. A different class of points over here. It seems pretty obvious that we could draw a line in here that would separate those two classes, right? We've got one kind of data over here, or one kind of data point over here, and these are all similar by some, not only in their distance from each other, but they also all have the same class. And then we've got some data points over here, and they're all similar, and they also have the same class. And we can look at this and we can say, okay, well, there's an algorithm out there that can look at these and discern some kind of separation between the two. And then when we get a new point, we get some new data point that falls here, well, we're likely to put it into this class 2, if we're saying this is class 1 over here and this is class 2 over here. So we're very likely to say, okay, well, that is, let's say that's in class 2. Does that mean that it is in class 2? Well, we don't know. We'd have to check. And there is the potential to get it wrong. So let's make this a little more concrete with some kind of simple example. I often use this one because I think it gets the point across. Let's say that here we've got weight. Here we've got height. And we're talking about cats versus dogs. We've got two classes, cats and dogs. And let's say we've got a bunch of, like the majority of our cats are going to probably be down here, right? And then let's have dogs, and yeah, I'll use blue. And our dogs are going to be, you know, maybe there's some dogs in here, right? There's some smaller dogs. There's also some bigger cats, right? So we've got this thing that we can't easily draw a line through, right? There's no easy line to be drawn. But it's possible that there is an algorithm out there that we can use that will do one of a couple things. Like maybe it'll draw some like very linear line, and we're going to get it wrong on some predictions. If we get a dog over in this area right here, right, we get a new dog right there. Well, if we try to predict on that dog, we're going to get it wrong. And that kind of makes sense that we would. So there's some measure of success here that we can determine. We can talk about accuracy or precision, and we can consider that in terms of the performance of our algorithm. And in general, when we're looking at these machine learning algorithms, what we'll do is we'll set a benchmark. We'll say, well, we need to get 98% accuracy. Let's say accuracy is our measurement. And we'll keep working with our data and various models and tuning those models until we get up to 98% accuracy. That doesn't mean that that's the best we can do. That just means we have set, for our business intelligence, we've set some threshold that we need to do at least that well. And if we get to that point, we're good. We can walk away from it. It's a little bit hand wavy, but that's often what you do in the real world. You say, well, I'm going to try to get this to be able to predict with 98% accuracy, and if it does that, we're good. And we can update this model later. We can tune it. We can make it better. We can make it adjust to. We can rework it to adjust to updated data, things like that. But we'll set a threshold and we'll try to meet that threshold. So let's make this just a little more abstract for a second. This is something I mentioned before, but what a machine learning algorithm does, okay, the way we're going to think about this is that there is some space that is composed, that has elements that are functions, right, that can make predictions after they learn some data, okay? So we've got some algorithm that I'm going to represent as a box. We feed it data. And what this algorithm outputs is essentially another algorithm that is trained, right? This is our trained algorithm. And then we can give it we can give this second one a new data point. And it can give us a prediction. And that can be a continuous prediction, right? It can be a value, right, like 33. It can be a class, like cat or dog, right? It can be a vector of continuous values or a vector of classes. It can be a new image, right? It can predict an image. We've got networks, neural nets that can do that kind of thing. So in this process, here's our untrained algorithm here, right? This function exists in some space, and there is a subset of this space that has, various functions in it that will meet the level of our business intelligence problem, right? That will meet that threshold, whatever we set as a threshold. And we're only going to end up at the end of the day, let me modify that. We're likely only going to use one of these functions at the end of the day. And that doesn't mean it's the best function. It doesn't mean that it's the best approach. It doesn't mean that it's the best tuned. But ultimately, there is some theoretical phenomenon that can be described by a theoretical function, and we are not going to find that theoretical function, that perfect function that gives us the perfect prediction. Okay, we're going to assume it's out there, if only we knew. But what we're going to do ultimately, in most cases, we're going to select a single function, and we're going to use that to solve the problem at hand. Although we can have what's called online learners, right? Which are models that, given new information, they update themselves. That's also a thing that's commonly used. But you can think about that almost as being, well, F3 is migrating itself toward being F3 prime, a different version of F3, which is ultimately a slightly different function. But so with machine learning, we really turn the coding paradigm inside out. And what that means, if we're thinking about traditional coding, you start with a problem and you write a bunch of code to solve that problem. With machine learning, you start with the data, you apply an algorithm, the algorithm gives you a bunch of code to solve problems related to that data. So it's sort of like this inversion of the process. Obviously, you have to write some code in here somewhere. You need to write code to call the algorithm. That's something you'll have to do. But in terms of the amount of code written, we often will call this procedural, right? Procedural coding. And then there's, machine learning where you are invoking a learner. That learner learns the data and then is able to make, make predictions on that data, on new unseen data, ideally. So that's our kind of generality, right? That's where we're coming from. There are two, let's just say there are two types of machine learning that, I want you to think about. There's supervised and unsupervised. These are kind of cryptic, we don't really know what these mean. But this has to do with the data in a lot of ways. So in supervised learning, we have data that contains targets, right? We have a bunch of pictures of cats and dogs, and all the cat pictures are tagged with cat, right? And all the dog pictures are tagged with dog. And what the supervised algorithm is going to do is it's going to guess on a picture, and if it gets it wrong, it's going to adjust itself, and then it's going to guess on another picture. If it gets it wrong, it's going to adjust itself, and if it guesses right, it's going to be like, cool, and then it's going to keep doing that until it's trained. And at the end of this, we have an algorithm that, given a new picture of a cat, will reasonably predict that it's a cat, or it'll say, well, I'm 93% sure this is a cat, right? An unsupervised approach, our data has no targets, okay? So we just have data. And often what we're trying to do here is discern signal. And these kinds of algorithms, I'm really drawn to a lot of unsupervised algorithms. I think there's something that feels a little mystical about it, right? Like, what is the signal in the noise kind of thing? Are there clusters here? Is there something discernible? And I can't see it with my eyes, so can this algorithm see it? Now, often we will use unsupervised learners, unsupervised algorithms in order to gain insight into data that is also has targets. And from that, we will, engineer more features in our data so that we have better, a better prediction, better prediction outcomes. There are arguably other kinds of machine learning. There are things like generative networks. There's genetic algorithms that you can tie very closely to generative networks. But somewhere inside there, inside the other forms of machine learning, there's a supervised or unsupervised approach. And with that, on some level, we're trying to minimize or maximize something. And often we are, let's say minimizing error, right? Some kind of error. It could be mean squared error. It could be, just some difference between what we're guessing and the actual result. Or we're, maximizing or optimizing some kind of performance score. So, could be accuracy. We might be looking for the best accuracy or the best precision. If you want to think about some examples of this, I've got a few here. So what you might do with a supervised algorithm, you might predict miles per gallon based on vehicle descriptors like, size of the engine block, volume of the differential, whatever makes sense. You might be predicting customer churn, like customers leaving, based on prior data regarding customers leaving. You might be tagging images, right? So you have an image come up and you start labeling things in that image. That would be a supervised approach, right? That's based on prior images that were labeled. Unsupervised approaches, maybe you are looking at a bunch of customers, right, in a data set for your company, and you're trying to describe those customers based on kind of latent traits that they have. You don't really have a target there. You're analyzing this, and we often look at this as being exploratory. So unsupervised algorithms often are used in exploratory phases, or continually in an exploratory way. A lot of recommender systems like Netflix recommends you things, right? Hulu recommends you things. Those recommendation engines, well, it depends. Let's say it depends. There are generally some unsupervised approaches that are sitting under the hood of that. Often there's supervised approaches as well, right? Because you do have data in those environments. If somebody clicks on something, then they watch it, and you can say, well, it was successful. This recommendation was successful. And then you can, have a means by which you can compare your guesses against the actual results. Another unsupervised approach might be describing document topics based on word frequencies. I'm working on a project right now that is essentially this, right? Looking at a bunch of different individuals and describing their interests, but describing those individuals in terms of topics of interest, and the topics themselves are keywords in descriptions that they provided. Or grouping similar images together based on the morphology of the image, right? Like how it's composed, the salient features of it, anything like that. So let's think about what it means for a machine learning algorithm to be effective. And I think this is XKCD, and they can be really funny sometimes. This is one of my, I kind of love this, because if you notice, these are all scatter plots. In every one of these scatter plots, these are the same dots, right? And these are all different lines that are fitting these scatter plots. And it's like, I did a regression. I made a curved line. All of these look reasonable in a way, right? And, you know, you start looking at this and you're like, well, how do you know? You know, how do you know that your model is performing well? And this brings up, you know, fundamentally this leads us into the idea of cross-validation. Validation in general, when you see this term, you know, how do you validate your model? You know, validation, let's actually spell it. You're just verifying that the model is doing something reasonably well, let's say. Because it's a mystery if you don't have some rigorous approach. And I'm going to show you a way that we might do that. So I'm going to talk only about a supervised learning model today, and we'll continue this on Saturday as well. But let's think about just what this thing is: cross-validation. Cross-validation. So you always want to validate the effectiveness of your model, whether it's supervised or unsupervised. In general, if you have an unsupervised algorithm, one of the ways that you'll validate it is by looking at the results, like literally as a human looking at it. That's not always the case. There are stricter ways to do that. But in supervised learning, we do have a specific approach that we can use. So what we do, let's say we have a data set with 10,000 rows. The first thing we do is we split the data into into at least two parts, sometimes three, and we call one of those the training set. So we've got training, we've got, sorry, that's not that easy to read, sorry about that. Training, we've got, this will be a little bit better, validation. Training, validation, and then test. Today, I'm actually just going to do training and test. That's sort of an old school approach, but you know, because we have a lot more data these days, and so we'll usually do 3 sets. But just in the interest of keeping it simple, we'll make train and test. So you split the data, and then you train your model whatever model that is. It could be a linear regression, right? You train your model on the training set. While you're doing that, you adjust what we call you train your model multiple times, many times, for different sets of hyperparameters. Here's a fun new word: hyperparameter. All this means is it's just a tuning knob for your model. So you know, what we're going to look at today is something called k nearest neighbors. Well, we might start looking at that today. We might actually just do that on Saturday. But k nearest neighbors, you can change the value of k, right? And k in that sense is a hyperparameter. So you get this model, and there's a bunch of different settings, and then you train it multiple times at different settings. And you know, those different settings are different settings of your hyperparameters. So you do that, and then once you train your model on the training set, you validate it by testing the trained model on your test set to make you predict on the test set. So let's say predict on test. And you get some kind of metric out of that. You get, you know, an accuracy score for each model, for each trained model. And this is kind of mimicking the real world, right? You've taken your data and you're training on only this much of it, and you're testing on this, this test data is meant to look like the real world. You know, what this should do in production. And with that real world data, you are validating your training set. Because if you make predictions on things the model already knows, it's probably going to do pretty well. In general, it will, not always. But it shouldn't do as well on the test data, right? Because it's never seen it before. And, you know, this might raise some questions like, well, won't your model be better if you train it on everything? Maybe, you know, maybe. But you have no way to validate it if you train it on everything. So, you know, you can always get more data. Well, maybe. That's actually the biggest problem in most cases, is that you can't get more data. But your model will encounter new data out there in the world. We set the test set aside to validate the trained model. And then, you know, the last step of this really is you choose the most performant model, you know? So you just choose the best model with the best hyperparameters. And that's really it. Now, this may seem a little bit, I don't know, it's a little bit brute force, right? It's like, okay, we're just going to try this with a bunch of different settings, and whatever works best works the best. It tends to not be quite that simple, because you need to research your model, you need to find out about it, you need to think about it, and what you often do is you get on arXiv and you read papers about what are potentially some of the best hyperparameters for this model, given certain types of data. So you inform yourself from things that people have already done, and you engage with the larger scientific community as a result. Even if you're working on what seems to be, you know, fairly simple data in a fairly direct business situation, right? Predicting the sales of an item, you know, based on certain customer metrics, things like that. Well, you know, to tune your model, you are probably going to go read a few papers here and there, and that's just part of the environment, part of the culture of this work. So, let's take a break. Let's take 5 minutes, and when we get back, we'll start coding. We'll get into an explanation of cross-validation. Yeah. I'm going to put 5 minutes on here, and I'll see y'all back in a little bit. Okay. So I'm going to just start filling in a little plot here. And we're going to start considering a scatter plot, okay? And it's going to be generated. I'm going to generate that scatter plot from this general polynomial, okay? And I'm going to put in values for A, B, C, D, and big C here. And kind of the idea, well, let me just fill in these values and I'll explain as I go. So I'm going to generate some data, and then I'm going to create a model, or I'm going to employ a model that'll draw a line that follows the signal in that data. And then we'll talk about the problem that underlies cross-validation and why we solve it, essentially why we solve it in the way that we do. So you know what? Actually, I'm going to do this. I'm going to do 5x plus 3 plus 3. So notice we have this very simple representation of a linear, just a linear plot. It's just a simple line. Now I'm going to do 3x. Let's do 3x squared plus 5x plus 3, right? And I'm going to continue in this fashion. And this next one is going to be negative 0.2, negative 0.2x, cubed, plus 3x squared plus 5x plus 3. Notice those two aren't that different. And then the last one I'm going to plot is 0.006 x to the fourth plus this negative 2x cubed plus 3x squared plus 5x plus 3. Okay. So notice we've got a few different plots here, and I can kind of turn these on and off, right? So, nope. Okay, so let's look at 5x plus 3, right? If we're going to generate points around this line, we have a sense of what that might look like, right? Not too complicated to think about that. And 3x squared plus 5x plus 3. And we'll just look at this one. Now, consider this, right? Consider that this order 3 polynomial has two curves in it. And I just want to, point at this. This order 3 polynomial to the third power has two distinct curves in it. This one just has one. An order 2 polynomial just has one. And this order 4 polynomial, well, we're not going to be able to see it here, has the potential for three sort of changes in direction, right? And that's something that I'm going to refer to as complexity. The order of the polynomial I'm going to refer to as a form of complexity. The higher the order of the polynomial, the more occurrences of this variable x or transformations of this variable x occur. And we can think about that in terms of being complexity, okay? So I'm going to just set this aside. and kind of, you know, well, let's just get into plotting, because I think this will become clearer once we're actually looking at a scatter plot. So I am going to make this, so let's say a scatter plot, and the type of function we're thinking about here is, right, f of x is going to equal ax to the fourth, and I'm just going to copy this and change, plus bx to the third plus cx squared plus dx plus c. And I'll explain what I mean by c here in just a second. So c, that's b. Okay. So there we have this. We're going to think about C as being something like an intercept, right? In the way that we've always thought about it. C is going to be like an intercept. We're also going to think about it a little bit in terms of there's some irreducible error out there, but I'm not going to get too deep into that. I think we'll see that shortly. So I'm going to use Numpy. And Numpy is our, let's say, our linear algebra library. We get things that are like lists, but they're way better. How about that? And we can perform operations on every item in that list simultaneously, and that's where we get our linear algebra operations. We can add a number to everything in a Numpy list. How do you do that in Python? You say for item in list, that item plus gets 1, and you actually have to overwrite each reference. So it's for what item for index item in enumerate the list item or list sub index plus gets 1. You could do it like that, or in list sub index gets item plus 1. However we want to think about that. So Numpy allows us to do much more efficient calculations. You will not use lists as much in the DSI. You will default to NumPy, or you'll use pandas, for these kinds of things. And we need you to be good at lists in order to move forward, because that's classical programming. You need to know that in Python, but you will live much more in NumPy than you will in Python lists. So let's say we'll import matplot lib.pyplot as PLT. This is just a plotting library, and we're going to use that. So to make this scatter plot, I'm going to talk through this pretty quickly, I'll try to make it make sense as we go. But essentially, I am going to generate a bunch of points, right, in a plot, and then use kind of a built-in machine, just using a basic regression, essentially, that's built into NumPy. We're going to try to get this to happen. We're going to try to draw a line in that scatter plot. And then we're going to use that as to underlie the idea of why we need cross-validation, or why we have cross-validation. So I'm going to draw 50 points. That's our number of samples, by default 50. And I'm going to make this fit complexity 1. Now, what I mean by this fit complexity is the complexity of our model. And complexity here, again, think about that as the order of the polynomial. So with a fit complexity of 1, that's going to be a straight line that gets drawn through the data, no matter what, right? Even if the data is really curvy, if our fit complexity is 1, it's going to draw a straight line. And then I'm going to set the degree of the underlying function that generates our data, right? This is that secret function out in the ether that we don't know, that is impossible to purely discover, but we know what it is. It's going to be in this form that we're seeing up here, and I'm going to hard code it into an if-else structure. Okay, so I don't need to do this, but I'm going to say n just to be very clear. This is our number of samples. That's just a common form to see that in. I'm not modifying it or anything. It's just what I'm doing. And then I'm going to do this thing that many of you might be familiar with, but many of you might not. I'm going to make our random determined. And what that means is that I'm going to generate random points, but I'm always going to generate them in the same way. I'm doing that for a few reasons. But this is a very common thing for you to do in these processes, because you want to, if you're constantly looking at random stuff, and you change something and the output changes, how do you know? How do you know that the output changed because of the randomness or because of something you changed, right? So I'm setting a random seed to account for that. So we'll know that if we make a change, that's why we're seeing different output. And then I'm going to generate random values. The way I'm going to do this is using Numpy, and this is very convenient. I can generate n random values, np.random.rand. That's going to be n random values. Let's look at what that looks like. Why don't I just print x, and I'll call this function really quick. So that's what that looks like. These are all, you can see these are all floats. And I'm going to take those floats and I'm going to make them bigger. Oop. That doesn't make sense. I put that in absolutely the wrong spot. And now these numbers are bigger. And I think this is funny. It's like, well, let's, say that this is 1, 4, 8. We can ignore the e here. In fact, if we wanted to make these integers, that might make as much sense. But notice now we've got values between, ideally between 1 and 20, but not seeing anything above 10. Either way, that's fine. It's going to work for our purposes. So that's just a bunch of random values. That's our x values. And then we're going to want to plot those x and y, right? So that we have dots on a scatter plot. So the next part of this is to define the polynomial. And this is going to be very straightforward. I'm going to use the same values that I used in Desmos when I plotted it in that plotting the graphing calculator. So if the degree is 1, and notice this is the underlying function, the degree of the underlying function. If the degree of that underlying function is 1, then y is going to get 5x plus 3. This is like this is the magic of NumPy, right? This looks like absolutely looks like just math, but we're going to take that every item in that vector, every item in this vector, we're going to multiply each of these items by 5 and then add 3 to each of them, and that's going to be our y value. So you can see on this first one we're going to go 1 over, and then we're going to go essentially 8 up, right? So that's a point. That's a single point. And at the end of this, we're going to do that for every point in here, and we're going to end up with this y vector that has corresponding points to x. So that's if the degree is 1, and then if the degree is 2, and why don't I just do some copy paste here. If the degree is 2, then y is going to be 3x squared plus 5x plus 3. And then I'll change that to an elif. And then if the degree is 3, this is going to be negative 0.2 x to the third plus 3x squared plus 5x plus 3. And then if the degree is 4, oh, I only have a single equals here. Classic error right there. This is going to be 0.006 x to the fourth. And now if we were to print y, we could see that we have these values. We have these values of y. And I'll just do that. So why don't we just print y? There we go. Here are our y values. If I run this again, it should be the same, and it is. And if I change the degree of the polynomial to, say, 3, those will be different, but they'll always be different in the same way. And that's what we're looking for. Okay. So the next thing I'm going to do is I'm going to just insert some noise in here. And I'm going to, you know, we know a little bit about the normal distribution, right? Where, you know, we have this shape. I am going to insert Gaussian noise, okay? So I'm going to insert normal noise. And what that means is that we're more likely to get, if this is 0, we're more likely to get values around 0 than we are to get values further away from 0. And I'll just show you how I'm going to do that really quick. So, well, the first thing I'm going to do in order to do that is I'm going to get the range of y. So I'm going to get the range of y, and the y value range is easy to get through this function, ptp, of y. So I've got the range of y. Now I'm going to add some noise. So let's do add noise. And y is going to get, well, I'm going to take each point, okay? And I'm going to add to that point some random normal noise. Centered around 0, just like in that drawing I made. Centered around 0. And the scale of which is going to be, well, 1/10 of the y val range. And that's most of that. And then I'm going to do that for every point in y. So that is a comprehension. But notice how you can kind of talk through a comprehension. You know, I can just say what's going on there, which I think is kind of cool. For every point, I'm going to add some random normal noise centered around 0. So a little above or a little below 0. And it's going to be 1/10 of the range of y for every point in y. Okay. So now we can draw a line. Or we can define the line that we draw. So here's the drawn line. First thing is I'm going to get this fit complexity. I'm just going to give it another variable. I'm just being a little safe there. It's not completely necessary, but I'm just doing it. And I'm going to build this regression using something very simple in the, well, something very immediately available in Numpy, which is a poly1d. This is just a polyfit line. So np.polyfit, pass in x and y. And notice that I've overwritten y with noise, right? So even though initially we have this, we have points along a line, those have moved away from the line. And this np polyfit and poly1d, this is going to kind of build a line that best fits those scattered points, okay? So x, y, and then I'm going to pass in the fit complexity, which is a parameter of this polyfit line, right? If I want to pass in a very complex, if I want to try to superimpose a very complex, very curvy thing on this, I can do that. But, you know, currently, you know, by default, we have this set to just a simple linear fit. Okay. And then I'm going to, let's see, I think I'm going to do this for every unique value of x. Yeah, I think that looks good. Okay. So we have everything we need now, and we can plot this. This should work. So let's plot all of this. When you make a plot, give it a good title, give it good descriptors, give it everything it needs to be interpretable. Okay. So I'm going to do that. I'm going to make a title, and I'm going to say n. This is just the number of items, and maybe I'll do this as an f string. So we'll do that, and we'll say n is that, and then I'm actually going to do this on multiple lines just to keep it well organized. And I'm going to say data degree. So this is the degree of the underlying function, and this is our degree. And then we're going to do the fit complexity, which is named exactly that, the fit complexity. And is that good? That should be it. Yep, I think that's good. All right, and then I'm simply going to make a scatter plot of the x and y values. I'm going to set a color, and I'm going to set this value alpha, which is just sort of the transparency of the color. So I'll do that. And then I'm going to plot that regression line against x. So do that. And then this is just to show it. So let's see if that works. Oops, I need parentheses there. Okay, so that worked. And let's look at this. Let's get a view on this. So essentially what's happening here is we've got some lines, or sorry, we've got some data points, and they've arranged like this, and we've got 50 of them. And the underlying function we know to be of degree 1, and we're fitting it with a complexity, a function that has complexity of 1. And so we're just drawing a straight line right through that. Now, let's play around with this a little bit. What happens if we change the fit complexity to 4? We get some curvature in there, right? We get some curve in that fit line. Now, we know that the underlying function is, has a degree 1. But in the real world, you're not going to know that. And let's reduce this to 25 samples. This line looks reasonable, but we know better because we know better. But in the real world, you don't know better. And this, let's change this to 5 samples and see what happens. Well, that's great. We're just connecting some dots that, and we're like hard connecting them. We're like, hey, here's a great model to predict data here. Of course not. But, we would have to update this with more information. So I'm going to change this to 500. And notice that 500 actually smooths our fit line really well. And even if I change this, I'm going to change this to degree fit complexity of 20. That's still not doing the worst. It gets weird over here, but that's not doing so terrible. If we took this into production, it would predict pretty well on our data, on new data that's coming from the same phenomenon. I'm actually throwing a little warning here because of doing that, but if we take this down to 5, we're not even really going to notice a difference. So that might give you some intuition here that more data is better, right? Your model's probably going to do better if you have more data. Now let's change this degree to 3. And it turns out that a fit complexity of 5 is going to perform pretty well on data that's generated with this underlying function that has that's an order 3 polynomial. But I want to just point this out. If we fit this with if we fit this with a complexity of 2, if our model has a complexity of 2, that seems to be doing reasonably well. And especially if we have much fewer samples, right? We don't know any better, right? We don't know, in this case, if 3 would be better than 2. It looks like 2 is fine. What we do know, or what we will know in a second, is that 1 is just not doing good at all, right? We're just cutting a line right through that. And when we see this, what we might say about it, I think a good way to think about this is that this is very opinionated, right? This model has a pretty strong opinion about what's going on there, and it's getting it wrong. But the term we actually use is it has high bias. It's a very biased model, and it's getting it wrong because it's not flexible enough. And what we also might say, well, here we've got this fit complexity of 1. Let's go back up to a fit complexity of 20. And what we can see here is that this model gets it wrong in a different way, right? It gets it wrong in quite a different way. It's just trying to connect the dots. And what we might say here is that it's flexible. We might say that this model is very flexible, but we also might say that this has high variance, okay? So it's following the variation in the data. It has high variance. And ultimately, our ideal is probably going to be, having an order 3 fit on a degree 3 underlying phenomenon, but this order 2 fit is just fine. And this leads us to a concept that most of you probably heard of before. We have Occam's razor. And the way that we will think about this is that if a more complex model doesn't outperform a simpler model, and more complex here we could just say is higher order polynomial, if it doesn't seem to outperform a simpler model, then choose the simpler model, right? And we can apply this in a number of cases. So the takeaway would be choose a simpler model that performs well, that still performs well. And another way that you can think about this is, let's say you've got some data in front of you and you build a 1D convolutional net, and it's awesome, and you train it on this data and it predicts really well, and then you compare it to you have this really low error, right? Very low error on your continuous predictions. And then you compare that to a linear regression, and the linear regression has slightly more error, just the tiniest bit more error. And you're like, well, technically this really complex network is outperforming the linear regression, but not significantly. And you could test that significance. You could see if it is actually significant in light of how much data you have. But you should just pick the simpler model, right? A linear regression is just going to be this instant thing that you can retrain constantly. And if your phenomenon is that simple, well, great. Choose the simpler model. And out of that, you can interpret it easier as well. You can say, well, this is why this works this way. So that's the concept of Occam's razor for us in this case. More colloquially, it's like, well, when given a bunch of explanations, you're given, some explanation that's very conspiratorial and obtuse and really complex. And then somebody else is like, well, it might just be this really simple thing. It's more likely the simple thing in those cases, right? It's generally not going to be the large conspiratorial explanation. It's often going to be the simpler explanation. And so, you want to think in terms of Occam's razor when it comes to these models, right? Does a simpler model effectively explain the data or discover a signal in relation to a more complex model? And if it does, you should choose the simpler model because it gets the job done just as effectively, and it's likely to be less expensive in terms of time, in terms of energy, in terms of everything. Okay, so this is kind of the basis for the idea of cross-validation. How do we actually systematically choose this? Well, like I said, we split our data and we measure the performance. Maybe in this case, we would measure the error, right? We would, I'll just kind of describe this on the fly. We might look at our line and measure the distances between each data point and the line, right? So we've got a little tiny distance there, there. And we would, sum. Oh, well, whatever. Oh, I can't actually undo when I draw on this thing. That's fine. We would sum the error for each point versus each prediction, right? Because we can imagine that for this point up here, this is the prediction, right? That's where it should be, quote unquote should be according to our model. And we would square that and then divide that by n. That's actually our MSE, or mean squared error, right? That's the average error, the average squared error. And we can see that right here. So yeah, we would seek to minimize that. We would seek to minimize that, but we wouldn't seek to minimize it on the data that the model already knows. We would get some new data out here. We would get, let's say we've got this value 13 over here, and, well, 13 predicts to be, maybe 13 predicts to be out here. Well, that would be one of the distances that we measure, and maybe we get it right a number of times, and those are close to 0, and then we get it wrong a number of times, and we just sum and measure all these, and whatever version of this model, right, this blue line minimizes these errors, we will likely want to go with that. That should be the best one. But notice this has to be on new data. It has to be. It can't be on the training data because the model already knows the training data. Okay. So with that, let's get into the idea of a machine learning workflow. I'm simplifying this just to be clear. It's going to be, I'm going to make this simpler than what you might even learn on, in the first couple days of the DSI. But this is a general pattern, and different people will structure it a little bit differently. But at the end of the day, it's basically the same thing. This is going to be on a supervised problem, right? And I'm just going to call this apply cross-val to a classification problem. Okay, so what do I mean by classification? That's simple enough. We can kind of categorize supervised problems into two different types of problem. We've got classification and regression. And it's kind of unfortunate that we use this word regression here because there's a thing called a linear regression, and that's not what I'm referring to here, although a linear regression does do the thing I'm referring to here. But when we think about classification, we're predicting a class, right? We're predicting it's either a dog or it's a cat. And with regression, we can think about it in terms of predicting, let's say, the value of a stock. One of these things is categorical, right? Dog, dog and cat, those are just categories. And so we're predicting some class of outcome, whether it's dog or cat or panda, right? With regression, we're predicting a continuous value. We're predicting a numeric, I'm going to say numeric value, and generally this will be continuous, or continuous is insofar as a computer can be continuous, because we are calculating an error. In regressions, we tend to optimize by error calculation, right? How far are we away from the prediction? In classification, we tend to optimize in terms of, did we get it right? Right? How many times did we get it right out of how many times we tried? How many times did we get it wrong out of how many times we tried? How many out of the amount of times that we got it wrong? There's just all these different questions, right, that we can potentially ask. We can have false positives, false negatives, true positives, and true negatives, and all of those sort of have their different. Those are all possibilities in terms of classification. Regression is just that single numeric output, that distance at the end of the day. So we're going to work on a classification problem, and we're going to use a classic data set called the Iris data set. It's a toy data set. There's a bunch of these. We can just Google sklearn toy datasets, and here are the various toy datasets. So we've got the Boston house prices dataset. Everybody knows that one. We know the Iris dataset, diabetes dataset, the digits dataset, which is literally sometimes that's called MNIST. We've got, I've never actually looked at this one, the physical exercises dataset. Never looked at that one. But these other two I know, the wine data set and the breast cancer Wisconsin data set. So these are all toy data sets. They're reasonably clean. And what I mean by that is data is almost always really dirty, and these are just easy to use. So you can quickly take them and leverage them against some problem and test out a model, play around with it. So the model that we're going to use is called KNN, which I think of as being a very simple, a naive algorithm. In fact, we don't even directly teach it in the DSI. There are a couple algorithms we don't teach in the DSI that are, sort of very simple, very basic algorithms. At some point, you're expected to know them, but they're really direct. In fact, if I gave you the algorithm itself to write, you could probably write it. Most of you could probably write it given a few hours. You could probably code through the whole thing. It's not that hard. So we're going to apply KNN because it's simple. It's also kind of weird, and I think that's nice to see. And then we'll use crossval, which I'm simplifying. So we're going to use a simple crossval. All right. So let's talk about aspects of KNN. KNN means K nearest neighbors. All right, so we've got KNN. This is K nearest neighbors. And there are some interesting things about this. We're going to approach this with simply x and y data. Okay. We're just going to use two features, and when I say features, I just mean x is a feature, and well, let's think about it this way: x1 and x2, and then y is the class. That's more accurate. So in this data that we're going to be using, we've got three classes. There are three different types of irises, and let's think about this in terms of three different colors, and maybe I'll make these a little bigger, just to make them a little easier to discern. And do that. Oh, no, I don't want any of that. Okay. Oh my gosh. Just stay normal. Okay, you know what? Give up on that. So these might be a little bit hard to discern, but we're going to think about them. Maybe they're somewhat easier to differentiate because of the size and shape, which is my goal. Okay. So what KNN is going to do is for every one of these items, it's going to try to classify that item based on the k nearest neighbors. So if we look at this point right here, and we have a k of 3, let's say we have a k of, I'll put it down here, k of 3, then we're going to look here, here, and here. And unfortunately, those are three different items. So we're maybe going to just make a random guess, or we're going to take the closest one, and we're probably going to predict that it's that one. And we're going to get it wrong, which is okay. And then let's say we look at another one of these. Let's say this one, just so that we can get it right. And we're going to look at the three nearest neighbors. And I think that's them. And out of those, well, we're likely going to predict, well, we are absolutely going to predict that we're going to predict the correct class, right? And it's kind of a neat approach. So we do this for every data point. We just look at the closest thing and we predict, hey, let's take a vote. And if the three closest things are all the same, obviously we're going to predict that class. If if two of them outvote the other one, then we're going to take the class of those two, like we did here. So that's what we're seeing. Very simple, right? There's a weird thing about this, though. This is what we might call a non-parametric model. There's kind of nothing linear happening here, right? This is just each one of these things kind of lives in its own space, and as a result, there's no single line that we construct to draw through this and make separations. We've got some very strange manifold that allows for these votes. That manifold is sort of relative to each point, and that's kind of really amazing. I think this model, as simple as it is really, really cool. It turns out, though, that the model itself is basically the data. It's just how we think about it, right? We're not doing much here. We're just looking at each data point and looking at a couple other data points and making a vote. Turns out this is also very computationally expensive because we have to go through each point and look at every point in K. We have to look at K points within distance of every point. And that tends to be pretty expensive, especially if you have a high value of K or if you have a lot of data points. So the whole model, all your data has to live in memory at any given point, which makes it sort of impractical for a number of problems, although we do use this model in some types of simpler problems where it performs really well. So let's write this algorithm just in algorithmic language. I'm going to end up importing this from the sklearn library. But so like given, let's just say given data, we set a value of k, and then for each data point, we're going to find the k most similar data points. And then we check the class of each of those, of each within the k. And then we assume the point in question, right? We assume the point is of the majority class. So that's kind of cool, right? This is very simple. You can even think about how to do this just procedurally. You can. I have confidence that any of you, given a chunk of time to devote to this and maybe a little bit of help here and there, could code this out. And the maybe missing element here, though, is this idea of similarity. So let's think about similarity really quickly. So let's think about distance and similarity. And I'm going to list a couple metrics here. We've got Euclidean distance, right? So Euclidean distance, we've been seeing this. That mean squared error looks like Euclidean distance to me. This is just, if we want to think about it visually, you have a point and you have another point, and you're asking, well, what is that distance? That is our Euclidean distance, right? Fairly simple. We also have, let's say, taxi cab or Manhattan distance. So taxi cab, Manhattan. This one's a little different, but it's very related to Euclidean distance. Imagine that we have some grid, right? Some grid. And what we're going to do, well, how long does it take to get from this point to this point? Well, it probably takes about that much distance. So Manhattan distance or taxicab distance, we don't go as the crow flies, right? We go around all the city blocks. So that's a type of distance. And then another distance metric we might consider, which comes up a lot in natural language processing, is cosine similarity. And this is a little bit different. I just want to mention it in a conceptual way to show that we have a lot of different types of distance. So let's say you have a vector, and it looks like this. If you have another vector that looks like that, let's say, and then another vector that looks like that, it turns out that these two are closer to each other, right, than are these two. And so the cosine similarity of this vector and this vector are that similarity is higher than of this one with that one. So those are just three kinds of distances. There are a lot more. So when we're talking about this algorithm, KNN, we're actually just going to use Euclidean distance because we have fairly simple measurements. So let's see. Let's talk just the beginning of this, the machine learning workflow. So we're going to follow, like I said, a very general approach. And I'm going to just call this a general ML workflow. And the first stage of this is the most time-consuming by far, in most cases. Not today, or not in what we're going to do. We're actually going to streamline this because we're using the Iris dataset. It's going to be really easy. But in general, importing, cleaning, reshaping the data is the most time-consuming thing that you'll likely do. We kind of include in this a little bit of the exploratory phase. Often we'll think about what's called EDA, exploratory data analysis. We'll think about it in this phase because it goes well with the cleaning and reshaping of the data. So, EDA, which is exploratory data analysis. This tends to be the most time-consuming thing. So if you're in Jupyter, you can, and you're running Jupyter locally, you can actually use, if you're on a Mac or on a PC, on a Linux machine, you can actually list items in your directory using ls. And notice I've got some stuff here. I have items in the data directory. I have this thing iris.data.text. These are called magic commands. It's just bash commands that you can run within Jupyter, and they'll access your system. So that's kind of cool. And let's just read in this data really quick that I have in iris.data.text. So I'm going to use pandas to do this. When you're in the DSI, pandas is going to be your primary tool set for exploring data. It's really powerful, gets you a quick look, and it's pretty amazing. So I want to show you really quick what this data looks like in the terminal. So I'll go into data. Notice here's iris.data.text. I'm going to look at the top of this. And this is the first line of the file. Notice we don't have any names for these columns, okay? So I'm going to superimpose the names that should be there. Well, the names that are not included here. And this isn't uncommon. You might find data that you have to find some other key, that will tell you what each column means. And there are times, this is kind of amazing, there are times, this is in modern times, where there is no key, and you have to email somebody to find out what the columns are, right, of some data that's publicly available. And this is not out of the ordinary. You'll find yourself every once in a while, you're like, I don't know what this is. It says it's this, but that doesn't make any sense. And you end up emailing somebody, and they're like, oh yeah, that just means this. And you're like, you could have just put that, anywhere in relation to the data, just a README attached to it. Doesn't, it's not a big deal, but this is something in the world that is the problem that's not solved, right? At all, is the human's ability to communicate about the thing they're doing. We just have not even started to come close to that, right? So I'm gonna just define these names. All that said, we've got the sepal length, the sepal width, the petal length, and the petal width. And from that, when I load the data, which I'm going to do right now, I'm going to load this into a data structure called a data frame, which is a pandas data frame. That's the primary data structure for pandas. I can just read CSV. There's another one, read Excel. If you have spreadsheets and you want to open them up in pandas data frame and play around with them, you'll start to really love pandas, because everything that you wish you could just easily do with Excel, you can do that and so much more with pandas. So at this point, we have our data. I'm actually going to collect these column names into another variable called columns, even though, you know, I could just call df.columns or use names, but just following a common paradigm I have. And let's look at the first 10 entries of this. So I'm using this df.head function, and we have a data frame that we can look at. So our sepal length, sepal width, petal length, and petal width, and there's, oh, we're missing something. So it actually turned these into indices. It's because I didn't put the class in here. So let's run that again. So now that looks better. So notice now we're indexing starting at 0 instead of 5.1, which makes a lot more sense. So sepal length, sepal width, petal width, and that observation is an iris setosa. There are 3 different classes that we have here: iris setosa, iris versicolor, and iris virginica. And yeah, let's stop here. And let's see. The next thing we're going to do, we're just going to play around with this a little bit at the beginning of next class, and then we're going to take this data set, plot the features of it, and then run it through the KNN algorithm and talk about cross-validation through that lens. So that'll be the first plus, you know, part of our Saturday class, and then the rest of the Saturday class we'll look at the type of problem you might see. We'll talk about the technical interview, and we'll do a couple. I'll run you through a couple coding problems that look like something you might see on the technical interview. So that's class for today. Stay on if you have any questions. I'm going to stop recording.